Hello! Today we are going to be looking at metallic bonding. And so, as opposed to ionic bonding, where it was a metal and a nonmetal, today we're going to look at metallic bonding where it's simply just metals together. So to review, in an ionic compound, we said we could predict the dot structure and figure out what ion is going to be and name each one. So real quick, give that a try, pause it. You got them. Yeah, so aluminum's going to have 3 valence electrons, going to make a +3, and then be the aluminum ion. Phosphorus is going to have 5 valence. It'll gain 3, be a 3 minus. That is a phosphide ion. Beryllium has 2, so it's going to be a 2 plus and be a beryllium ion. And chlorine is going to have 7 valence, and so it's going to gain 1 to be a 1 minus ion in the chloride ion. Another review, we could think about how these are going to combine together, the structures and the formula they'd make. Go ahead and give that a try quick. You got it. Nice job. Yeah, sodium's got 1 valence and iodine has 7, so the 1 is going to go from sodium to iodine, and it'll make a 1-to-1 ratio, NaI. And calcium has 2 valence, chlorine has 7, so you're going to give 1 from calcium to 1 chlorine, but you still have 1 left, so you need a second atom of chlorine, and so that's going to receive the second electron from calcium, so it'll be CaCl2 for the chemical formula, because you need 2 chlorines for every 1 calcium. And again, remember that those are in a big ionic crystal, and it's the lowest ratio of them. When we talk about metals, though, what we're talking about is this idea that you have your positive nucleus and kind of the core electrons, and then the valence electrons are on the outside. Usually they have like 1 or 2 or 3 valence electrons, generally, not that many more of them. And what happens is that the metals, each atom of metal, the electrons are what we call delocalized, or they're kind of free floating and drifting around. What ends up happening is that the electrons are not really on one atom, but they belong to the entire group. And so we call that the sea of electrons, that there's just the electrons can move freely between the entire group, that they're not on any one particular atom. And so that's kind of important, because then when we look at what happens if you were to hit it with a hammer, hit it like where this says force down, like bang, what's going to happen is, as long as it stays connected to the group, the electrons aren't really on one atom, and so the attraction is between the positive ion and the negative group of electrons. Where if we were to hit a salt, an ionic compound, with a hammer, bang! Well, if we knock that down a little bit, now look, negative, I was using my finger, that won't work. Negative and negative here are now next to each other, and that's going to repel. So as soon as these are not next to each other, they're going to repel and break, shatter apart. Where metal, we can hit it, and as long as it stays connected to the group, that's why it's much more malleable, or we can hit it with a hammer and it'll tend to bend but not break. So as we think about this, we're thinking about really these electrons being shared to the entire group. It's kind of like if you walk to the playground, in your neighborhood playground, who owns it? Well, the neighborhood, right? It's not any one person's. The kids from all over the neighborhood can come and play on the playground, and that's an attraction for all the houses nearby. Is they're attracted to the playground. That's a selling point, is being close to the park for somebody's house. And so the free-flowing electrons, the sea of electrons, is attracting all of these positive ions and keeping them in kind of a crystalline structure. And so because of that, again, we can push them into a wire, draw out a wire from a metal rod. The we call that ductile, and that's again as long as the metal stays connected to the group, it still has that attraction to the sea of valence electrons. One cool thing about metals, though, is that it doesn't matter what ratio they form in. Remember how ionics, we said for every 1 calcium there has to be 2 chlorines because they're giving and taking electrons. Well, here it's kind of like the atoms are just sending electrons to the sea, and doesn't matter if they send 1, if they send 2, if they send 3. It doesn't matter how many kids are at each house around the playground. They're all going to come to the playground, right? And so there's really no ratio at which the metals have to form. And there's no limit to how many of them. It's close to almost 100 different metals. You could use all of them, or 1 of them, or 3 of them, or 5 of them. Anytime we mix them together, that's called an alloy. And we can mix them in any ratio you want. So there's like literally infinite, practically, not even practically, literally infinite number of alloys that are out there. And a cool thing about alloys is that changing some of the composition of them can have a huge impact on their properties. So here's stainless steel. Steel is not a pure substance. Not all steel is the same. There are some steels that are better than others. And so stainless steel has these percentages generally, different kinds of thing. Sterling silver, if you've ever heard of like someone having to polish silver back in the old days, it's because silver by itself tarnishes. It gets this green coating on it, it reacts with oxygen. Where sterling silver, if you put a little bit of copper in it, it's harder, it's more durable, you don't have to polish it. You probably do not have actual silverware in your house because it's kind of a pain. But we've made some alloys that have better properties now. And so cool things out there like to be discovered. Like if you change a little bit of the composition of it, it actually changes the entire property. So there's really not a lot of pattern to it either. And so there's not a lot we can say from a chemistry, looking at it, an overview chemistry perspective, to look at any kind of pattern or property with it, or at least not one that's been discovered yet. Maybe you'll be one to discover a pattern of these alloys and see, we haven't found it yet, if there's any predictable patterns within it like we can with ionic and covalent bonds. So, alloys and metallic bonds, the sea of electrons, it's a big deal. Have a great day.